Here I present Point-NeRF, point-based neural radiance field. This work is conducted by University of Southern California and Adobe Research. The original NeRF model optimized the scene by taking hundreds of multi-view images. Along each camera ray, NeRF samples hundreds of shading points, even most of them are in empty regions. During shading, NeRF encodes the entire radiance fields as MLPs, which take the shading location and ray direction and output the RGB color and the volume density. Since NeRF is unaware of scene geometry, its shading sampling is inefficient. Using a single network to encode the scene also makes it hard to scale and converge. To address these issues, we leverage multi-view reconstruction method to quickly reconstruct the point cloud. Point-NeRF then install the neural features on each point and obtain a neural point cloud. During remarching, Point-NeRF skips all the empty regions and only computes shading near the geometry prior. This efficient sampling strategy differentiates Point-NeRF from previous NeRF models. Once the ray arrives at the nearby regions of the geometry prior, Point-NeRF creates k-nearest neural points and uses their relative positions, their point features, and ray directions as input to compute the RGB color and volume density. The efficient sampling strategy, the radiance field localization, and the flexibility of the points help Point-NeRF achieve fast convergence, high rendering quality, flexibility for editing, and strong scalability for large scene. To get the shape prior from the 2D image's input, a multi-view reconstruction network generates depth images and combines them into a point cloud. We can also use an existing point cloud here. Then, another feature extraction network projects the image features onto the points and finally create a neural point cloud. During optimization, we only sample the shading points near the shape prior. For example, XA, XB, and XC. The k-nearest neural points are queried, and their features are aggregated according to their relative positions to the shading location and the scalar value, point confidence. The MLPs use the aggregated features to generate view-dependent colors and volume density. After aggregating the radiance along the ray, we can calculate the rendering loss between the generated and the ground truth color on the pixel. The gradients will optimize not only the MLPs, but also the point features. We also propose point pruning and growing techniques to address outliers and holes in the initial point cloud. Here we have an outlier point, P1. Since its point confidence, gamma 1, will be driven to 0 during optimization, we can prune these outliers and improve both the point cloud and the rendering results. Suppose a ray passes through the hole. If our model predicts high volume density at the shading location and its neural point neighbors are relatively far away from it, we can confidently add a new point at its location. The process can expand the boundary of our point cloud to fill the holes and improve the final results. Since the radiance field is distributed as point features, a local representation without the limitation of resolution, Point-NeRF can encode more fine-grained details and high-frequency information, thus finally achieves better rendering quality than NeRF, sparse voxel-based NeRF methods, and other point-based rendering methods. Point-NeRF also achieves a convergence speed which is 30 times faster than NeRF. On other datasets, such as DTU and Tangent Temples, Point-NeRF also consistently achieves high-quality rendering results with fast convergence speed. Because our point representation skips all the empty regions and only encodes radiance fields near the surface of objects, Point-NeRF is scalable to large-scale scenes such as ScanNet. Here we also demonstrate the effectiveness of point growing. With only rendering loss, Point-NeRF can even grow out the entire chair from only 1,000 initial points. Please visit our poster station for more explanation and insights. Thank you.